Hi, everyone. Hope you all are staying safe. So let's start our discussion from vertical and horizontal asymptote and slant asymptote, catching up from the last class. So as we have learned, if we have a rational function in its simplest form, then the line x equals c will be vertical asymptote for which the function f either increase or decrease without bound as x approaches to c. So mathematically, we find the vertical asymptote by setting the denominator of any rational function from its simplest form equals 0. And for the horizontal asymptote, the line y is equal d is the horizontal asymptote, the graph f, if the graph f approach to d as the x value increase or decrease without bound. Mathematically, how do you find horizontal asymptote? We compare. So we compare the degree of the numerator with the degree of the denominator, right? So if the degree of the numerator is smaller than the degree of the denominator, then the f has a horizontal asymptote y equals 0. If the degree of the denominator is equal to the degree of the numerator, then horizontal asymptote is the ratio between the leading coefficient of the function. If the degree of the numerator is higher than the degree of the denominator, then the graph has no horizontal asymptote. Okay. Then we have learned about the slant asymptote as well, which we call oblique asymptote as well. So first of all, we need to check if we have a slant asymptote for the rational function or not. How do we do that? We check if the degree of the numerator is exactly 1 degree higher of the degree of the denominator or not. If the degree of the numerator is exactly 1 degree higher than the degree of the denominator, then our function has a slant asymptote. And then if it has a slant asymptote, how do we find it? To find an equation for the slant asymptote, we divide the numerator by the denominator. And by dividing the numerator by the denominator, we'll find a quotient that is linear. And the slant asymptote will be the equation y equal the quotient that we have found. All right. Now we'll move forward and we'll look at this example and we'll try to find all the asymptote out of this function. Okay. So this is our function f of x. We have x squared plus 1 on the top, x minus 1 on the bottom. So first, vertical asymptote. So is this function in most simplest form? Yes, it is. We cannot factorize the numerator and the denominator anymore. So it's in most simplest form. So from this, now the denominator will give us the vertical asymptote by setting it equal 0. So we'll get x equal 1. This equation, this vertical line is our vertical asymptote. Next, horizontal asymptote. Let's check the degree of the numerator and the degree of the denominator. Degree of the numerator is 2, degree of the denominator is 1. So here we get n greater than m. So if the degree of the numerator is higher, then do we have any horizontal asymptote? No, there is no horizontal asymptote. Next, slant asymptote. Do we have any slant asymptote? So again, the degree of the numerator is exactly 1 degree higher than the degree of the denominator. So Yes, we do have a slant asymptote, right? Now we'll find the slant asymptote by dividing the numerator by the denominator. So it's a polynomial division that we tried in our last class. So what do we multiply with the dividend to get the leading term x squared? X. So if we multiply by x, we'll get x squared minus x. Now subtract from the top. We'll distribute the negative. We'll get negative x squared minus 1. And so the x squared will get canceled. And this will become positive. So we'll have positive x here. And now we'll take this 1 down. So x plus 1. Now can we divide anymore? Yes, we can, because this polynomial here is not yet lower degree than the dividend. So what do we multiply with the dividend to get x? Positive 1. If we multiply, we'll get x minus 1. Now we'll subtract. The x will get cancelled, and we'll have positive 2 as a remainder. Now, the quotient x plus 1 is our slant asymptote, right? So y equal x plus 1 is our slant asymptote. Graphically, this black line represents the vertical asymptote, this purple line represents the slant asymptote, and the blue curves are our graph for the rational. Excuse me. Right? Now let's move forward. Here are our next example. We are trying to see, here actually we are given the graph of a rational function. We are assuming all the asymptotes and intercepts are shown in this graph, and the graph has no hole. So we'll use this graph to collect or complete all these following questions or following informations. The first question, find all x-intercept and y-intercept. So let's see, do we have any x-intercept? Is there any place where the graph is crossing the x-axis? Yes, it does. Here, right? And what is this coordinate point? That's 2, 0. That's our x-intercept. Now, do we have any y-intercept? Again, this black vertical dashed line are our vertical asymptote. The black horizontal dashed line is our horizontal asymptote. Okay, now do we have any x and y-intercept? Is there any place where the graph is crossing the y-axis? Yes, where? Here. And in terms of order pair, that's 0, 1. Okay. Next, write the equation for all vertical and horizontal asymptote. Okay, so the first horizontal asymptote, this one is passing through -1. So the first vertical asymptote is x equal -1. The other one, this one, is passing through +6. So x equal +6, right? These are our two vertical lines. X equal -1, x equal +6. Now for the horizontal asymptote, this is our horizontal asymptote. And the equation for this one is y equals 0. Right? Finally, we are trying to find what is the domain and range of the function, and we'll write them in interval notation or union of intervals. So for the domain, as we can see, the domain is everything except these two vertical line. That means the graph is getting all the x values except these 2 points, right? And these 2 points are -1 and +6. So domain will be all real numbers except these 2 points where we have vertical asymptotes. Okay, there it is. negative infinity to -1, union -1 to 6, union 6 to infinity. Now range. So as we can see, the graph is getting all the y values here, the bottom part here, the top part, and in the middle, everything. So the range will be all real numbers, right? Okay, let's move forward to the next problem. So here we are trying to graph this rational function. So again, to graph this rational function, we'll find all the asymptotes first. Okay, so now to find all the asymptotes, let's check if the function is in simplest form or not. So can we factorize the numerator anymore? It's quadratic with 3 terms. The constant term is 1. The middle coefficient is -3. Actually, we cannot factorize anymore. Okay, so if we cannot factorize anymore, that means that's the most simple form that we can have. So now from this simple form, we'll find the vertical asymptote by setting the denominator equal 0. So we'll get x equal to is our vertical asymptote, and there you go, the vertical asymptote in our graph. Next, horizontal asymptote. So the degree of the numerator is 2, the degree of the denominator is 1. So the degree of the numerator is higher than the degree of the denominator. And if that happens, then we do not have any horizontal asymptote, right? Finally, slant asymptote. Do we have any slant asymptote? Again, the degree of the numerator is exactly 1 degree higher than the degree of the denominator. So we do have a slant asymptote. Now to find the equation of the slant asymptote, we'll divide the numerator by the denominator, right? So let's divide the numerator by the denominator. What do we multiply with the dividend to get x squared? X. If we multiply by x, we'll get x squared minus 2x. Then we'll subtract the x squared will get cancelled. And here we'll have positive 2x. On the top, we have negative 3x. So we'll have negative x down here. And we'll take this 1 down. Now here, the leading term is negative x. So what do you multiply with x to get negative x? -1. And if we multiply -1, we will get negative x plus 2. Then we subtract. Again, negative x, and it will become positive x. This will cancel. And positive 1, and this will become -2. We'll have -1 as a remainder. So the quotient x minus 1 is our slant asymptote. Y equal x minus 1 is our slant asymptote. X minus 1. All right. Now I'll try to graph the slant asymptote. The y equal x minus 1 will be a slant asymptote like this, right? I hope we know how to plot this line. We can just randomly pick some x value and we'll find a y value. Just 2 order pair is enough to graph it. Yeah. Now, since we have our vertical asymptote, our slant asymptote, we'll graph the rational function. To graph the rational function, we'll pick some point from both sides of the vertical asymptote, and we'll see where do we get the order pairs that will lead us to plot the graph. First of all, let's pick the point x equal 1, and then for x equal 1, we'll see what the y value we get And based on that, if our point up here somewhere or down somewhere here, then we'll know if our graph is going on this part or in this part. Okay. So if we pick x equal 1 and plug in x equal 1 in the function f of x, we will get the y value is 1. That means the order pair is 1, 1. And the point order pair 1, 1 is up here, right? So our graph will go on this part. Next, we'll pick another point, let's say 3, and we'll find the x equal 3. We'll see what is our y value, and that will help us to know how the graph is going to look like for the right side of the vertical asymptote. So for x equal 3, the y value we get is 1. So the order pair is 3, 1, which is right up here. That means that helps us to know that the graph on this part will look like this. All right, that's it. Okay. Now we'll move forward to our next problem. Before moving forward to our next problem, here, let's talk about something else. So note that our discussion of asymptote requires the rational function is in the simplest form with no common factors between the numerator and denominator. Suppose a value is not in the domain of the original form of the function. That means, let's say for some certain value e, q of e equals 0. However, after factoring, the common factor x minus e cancels from the numerator and denominator. Okay, that means if we have a rational, if we factorize the numerator and denominator, and we get some common factor in between the numerator and denominator, so this factor get cancels, right? The factor that gets canceled will give us a whole for the graph. Okay. So now next example, we'll see. We'll try to graph it, find all the asymptote, but again we'll see that if there is any factor getting canceled from the top and the bottom, because if it does, then that factor will give us a whole. Okay. Now from the numerator, what is the common factor? From the numerator, the common factor is 3, negative 3x. Yes. And in the denominator, we have a quadratic. So we'll factorize the quadratic. The constant term is 10, and the middle coefficient is positive 7. So what would be two factors that will add, of 10 that will add to 7? 5 and 2. Yeah. Okay. So from the numerator, let's factorize the common factor negative 3x. We'll have x plus 5. From the denominator, we are factorizing, and we'll get x plus 2 times x plus 5. Now that's not in most simplest form. We have common factor in between numerator and denominator. So we'll cancel out the common factor and we'll get the simple form, which is negative 2x divided by x plus 2. But again, we have to be careful that this simplest form is for x being not equal to negative 5. That means the point that we are getting from the factor that is getting canceled. That's because we know originally for the domain, we look at the original rational function, right? And that's our original rational function in factorized form. And from this, we know in our domain, we cannot have negative 5 because that will make the denominator 0, right? Yeah. So while writing the simplest form, we'll carry this information with us for convenience. Now, from this simple form, we'll find the vertical asymptote. I mean, all the asymptotes, let's see. So the vertical asymptote will come from the denominator, x plus 2. Oh, sorry, first the whole. So the factor that is getting canceled is x plus 5 will give us the whole, right? So x coordinate of the whole. So if we set the factor x plus 5 equals 0, we'll get x equal negative 5. and that is our x-coordinate of the whole. And then we'll plug in -5 in this simple form to find the y-coordinate of the whole. So by plugging in -5 in this form, we'll get y equal -5. So our whole is at -5, -5 right here. Okay. So we do have a whole. Next, vertical asymptote will come from the denominator, x plus 2 equals 0, which will give us x equal -2. This line is our vertical asymptote. Next, horizontal asymptote. So the degree of the numerator and the degree of the denominator are equal, and that means the horizontal asymptote will be the ratio of the leading coefficients, which is -3/1, which is -3. So y equal -3 is our horizontal asymptote. And that was our vertical. Okay. Now, do we have any slant asymptote? Again, the degree of the numerator and denominator are equal, right? So we do not have any slant asymptote. So no slant asymptote for this function, all right? Now we'll try to graph it again. We'll pick some points for x from the left and right of the vertical asymptote. That will help us to know how the graph is going to look like in both sides. Okay, so here I have found some order pairs by picking some random x values and y values from the left and the right. So from the left, we picked negative x equal -8, x equal -4, -3. From the right, we picked -1, 0, 1, 4. And we plugged these x values in this simple form of the function to find the corresponding y value, right? So we found for -8, the y value will be -4. So for -8, -4 is here. -4, -6. So -4, -6, -3, -9 here. And that means the graph on this part will look like this. Okay, on the other side as well, -1, 3, -1, 3 is here, 0, 0, this one, negative, +1, -1 here, and 4, -2 is here, right? So on the right part, the graph is going to look like this, passing through these points. All right. Okay. So that's all for our topic on this rational function. So we will move forward and start our next topic a little bit. But again, please let me know if you have any questions on this. I do have office hour tomorrow. You can stop by my office hour with your friends, and I can work with you with any questions on the lecture or any questions on your homework. Okay. So I'll move forward and try to pull up the next lecture, our module 3. So our module 3 will contain exponential and logarithmic functions. So first of all, some warm-up questions. So here, as we can see, we have two expressions that we want to simplify. All right. Now, to simplify this expression, we'll warm up some exponential properties first. The first property. What is b raised to 0? So anything raised to 0, doesn't matter what the base is. Anything raised to 0 is equal to always 1, right? Next, what is b raised to negative n? So we can write b raised to negative n as 1 over b to the positive n, right? So this negative n indicates a reciprocal. Next, what we have, base b raised to m, base b raised to n, the base are equal. So how do we combine them? For this kind of case, with same base as a multiplication, we add the exponents. Next, what if in terms of quotient? For multiplication, we add the exponent. For quotient, we subtract the exponent. What if we have an exponent on the top of another exponent? We multiply the exponents. So as you can see, b raised to m times n. What if we have an exponent on the top of two different base? We distribute the base to everything that we have under parentheses, right? So this base will distribute to a and b both. So a to the m, b to the m. So here, the same thing. Here it was in terms of multiplication. What if we have a exponent on the top of our quotient? Same thing will happen. We'll distribute the exponent to everything that we have. So a to the m divided by b to the m. Next, what does it mean by a raised to 1 over n? So if the exponent is a quotient like 1 over n, something like this, that means it's a root. Yes, so that's going to be an nth root. For example, when we have, let's say, square root of a, what does the square root means? That's just a power 1 half, so on, right? Similar thing. Finally, if we have a power m over n, okay, how does that work? Actually, on the top of a here, we have two different kinds of exponent. All right, the m and times 1 over n. So this can be written as either the nth root first, and on the top, we have the exponent m, or we can apply the exponent m first, and on the top we'll have the nth root for 1 over n. Okay. Right, now by using all these properties, we'll try to simplify the warm-up questions that we have seen. So these are our warm-up problems. So we will apply all these properties. First of all, here we have exponent -3 on the top of everything under parentheses, right? So by this property and this property, we will distribute the exponent to everything that we have under parentheses. But before that, notice that we have another property, which is this one. If we have the same base with exponent m, exponent n as a quotient, then we can subtract the exponents to combine them. Here on the top, we have p raised to -2, and on the denominator, we have p raised to -5. So we can combine these two, right? And we'll subtract the exponents. So we'll have p raised to -2 subtract the other exponent, -5. So -2 and negative will become +5. So we'll have p to the 3, and the denominator is just the 4. Now we'll distribute this exponent to -3 to the numerator and denominator. And now while distributing, the p already has a power -3. So exponent on the top of another exponent will multiply the exponents. And 3 times -3, which is p to the -9. And the denominator is p to the -3. Now notice that both our numerator and denominator has negative exponent. What happens if we have negative exponent? What is the property? So the property for negative exponent is that it will become reciprocal, right? So the p to the -9 will become reciprocal as p to the 1 over p to the +9. 4 to the -3 will become reciprocal as 1 over 4 to the +3. So they are switching, right? And then 4 to 3 is 64. So that will be our final simplification. So the next problem, we have fourth root under we have x to the 3 and times sixth root with x. So by the property, the fourth root can be written as power form as 1 over 4, right? And the sixth root can be written as power form 1 over 6. And so that means if we have x to the 3, let me write it, x to the 3, and on the top for the fourth root, we have 1 over 4. Then exponent on the top of another exponent, we'll multiply them, and we'll get 3/4, right? Times x to the 6. Now notice that there is multiplication with the same base x. Now to combine them, we'll add the exponents. So we are adding the exponents 3 over 4 plus 1 over 6. Now there's a rational addition, so we'll need to find the LCD. The LCD for 4 and 6. For the denominators, it will be 12, right? And by getting the LCD 12, we'll add the numerators, we'll get 9 plus 2 on the numerator. So based on the LCD 12, if we want to make the first fraction 3 over 4 as the denominator LCD 12, we need to multiply both the numerator and denominator by 3. And for the second fraction, we'll multiply both the numerator and denominator by 2. So we'll get here 9 plus 2 on the top divided by 12, which will be 11 over 12. X raised to 11 over 12 is the simplification of this expression. All right? Okay. Now, this x raised to 11 over 12 can also be written as, that means it has x raised to 11 times 1 over 12, right? That means we'll apply either the exponent 11 first or the 1 over 12, both works. So if we apply the 11 first, we will have x to the 11 on the top. We'll have 1 over 12, which means a 12th root on the top of x to the 11. Okay? So that means if we end up with a exponent like this, a rational exponent, we'll convert it to a root format. Okay? I hope it makes sense. Now, moving forward, we actually have some more discussion for the exponential functions, logarithmic functions, how do we evaluate them, so on. Okay. So I'll just move forward to this slide a little bit to introduce you the exponential function. So let b be a constant, which is our base constant real number, and b is positive and not equal to 0. Sorry, not equal to 1. Then for any real number x, a function of the form f of x equal b to the x will be an exponential function with the base b and the exponent x. Now, if the base b is greater than 1, then f is an increasing exponential function, or we can call it exponential growth function as well. Okay, now notice that this one is the graph for b greater than positive 1. Now, if b is in between 0 to 1, what does it mean by in between 0 to 1? A fraction in between 0 to 1, right? Yeah. It can be 1/2, 1/3, 1/4, so on like this. Then the function will be a decreasing exponential function, and we sometimes call this one as exponential decay function. So this one will be the graph for b being in between 0 to 1, exponential decay function. The domain for both the exponential growth and decay, increasing exponential and decreasing exponential, the domain is all real numbers, negative infinity to positive infinity. The range, what are the y values, right? As we can clearly see, the graph, both graphs are all the time on the top part of the coordinate system, never getting in the down part. That means the range is always 0 to positive infinity. Yeah. Now the line y equals 0, this horizontal line is a horizontal asymptote for the exponential function, and the function passes through a point 0, 1, because for x value being 0 on any exponential function, if the exponent is 0, the functional value is 1, right? So yeah, so exponential function like this always pass through the point 0, 1. Okay. Now let's actually stop here, and in our next class we'll move forward and we'll start talking about more about the exponential function, logarithmic function. We'll try some examples, so on. If you have any question on this lecture, please let me know. The lecture for module 3 is already uploaded in D12, so you can move forward and try to see what's coming next, and let me know for any questions. Okay, so I'll stop here. Bye, and I'll see you in next class.